In this section, we start off looking at something called DC isolation. And you'll notice here in the diagrams, diagram A, instead of having an AC source, we have a DC source. Okay, you'll notice in B, we've got an AC source. And so when we turn the switch on or allow current to flow, the current will flow through the first coil, this primary, but nothing happens in the secondary. So therefore, we have no output off of the secondary. So if there's a DC in the primary of a transformer, nothing happens on the secondary. The reason is that a change in current in the primary winding is necessary to induce a voltage in the secondary winding. Okay, so then we mentioned that when we first started off, that we had current in the primary, induced voltage in the secondary. So therefore, the transformer isolates the secondary circuit from any DC in the primary circuit. A transformer that is used this way is strictly for isolation and has a turns ratio of 1. Okay, in the previous examples we had fractions 0.3, 0.2, 0.5, 0.4. Okay, in this case we have a turns ratio of 1. So we have one-to-one relationship between the two windings. Small transformers that are used then to isolate the DC bias from one stage of an amplifier to the next stage are called coupling transformers, because the AC signal is passed or coupled, but the DC is blocked. So there's a protection mechanism there so that we don't get any DC into the secondary. Coupling transformers are widely used at high frequencies where they are designed to pass only a select band of frequency. So they kind of act like a filter. Okay, they do this by making the primary and the secondary coils part of a parallel tuned circuit or a resonant circuit, which we saw earlier with LCs and RCs and different types of passive circuits. Tuned circuits are discussed later in chapter 17, and typically we get into that in the second semester. A typical transformer coupled amplifier arrangement then is shown in the diagram. Frequently the core of a coupling transformer can be adjusted to fine-tune the frequency response. Coupling transformers are also commonly used to couple a signal from an amplifier to a speaker. So this is the typical kind of circuit that you would see in radios and audio equipment. So we can see in the diagram here what we're talking about in terms of coupling an amplifier stage between 1 and 2 to achieve a coupling and an output. When a load resistor is connected to a secondary winding as shown, there's a current through the resulting secondary circuit because of the voltage induced in the secondary coil. It can be shown that the ratio then of the primary current on the left to the secondary current on the right, and it's equal to the turns ratio. So we saw this relationship earlier with voltage and windings. Now we have current in the primary, current on the secondary set up as a ratio to give us a ratio then N. A manipulation then of terms of the equation 14.6 then gives us this relationship where all we did was move our terms around so that we have being able to solve for the current in the secondary as the ratio of the primary current divided by N, okay, which shows that relationship. For a step-up transformer in which N is greater than 1, the secondary current is less than the primary current. For a step-down transformer, N is less than 1 and the current is greater than the primary current. When the secondary current then is greater than the primary voltage, the secondary current is lower than the primary current and vice versa. So in this example, we have two ideal transformers and they have loaded secondary windings. If the primary current is 100 milliamps, in each case, what is the load current? So in A, we have a 1 to 10 relationship, and in B we have a 2-to-1 relationship. So it's just a matter of plugging in the numbers in this simple relationship then, where we have 0.1 times 100 milliamps gives us 10 milliamps. For B, at a turns ratio of 1/2, the current through the load then is 2 times 100 milliamps, or 200 milliamps. Okay, so it's just showing you how to use the relationship to determine the loading then for the secondary. Okay, primary power equals load power. When a load is connected to the secondary winding of a transformer, the power transferred to the load can never be greater than the power in the primary winding. For an ideal transformer then, the power delivered to the primary equals the power delivered to the secondary by the secondary to the load. In a real or a lossy transformer, okay, so we've been talking ideal, now we're going to talk about what a real transformer looks like. When losses are considered, some of the power is dissipated in the transformer rather than the load. Therefore, the load power is always less than the power delivered to the primary. So again, got to remember, in electronics, there's no free lunch. There's going to be some loss somewhere in your circuit. It's, we don't live in an ideal world, and the circuits are always going to have some loss relationship associated with them. So when a load is connected to the secondary winding of a transformer, the power transferred to the load can never be greater than the power in the primary winding. For an ideal transformer, the power delivered to the primary equals the power delivered by the secondary to the load. So when losses are considered, some of the power is dissipated in the transformer rather than the load. Therefore, the load power is always less than the power in the primary. So you see all kinds of losses there occurring. Power is dependent on voltage and current, and there can be no increase in power in the transformer. Okay, there's no free lunch, and these are not Rube Goldberg devices. Okay, therefore, if the voltage is stepped up, the current is stepped down, and vice versa. In an ideal transformer, the secondary power is equal to the primary power regardless of the turns ratio. The power delivered to the primary then is power primary is equal to voltage times current, just like we've seen before, Ohm's law, and power law rather. Primary voltage, primary current. The power delivered to the load, P secondary, voltage secondary, current secondary. So we're back to Watt's law as it relates to transformers. The power delivered to the primary then is, as we saw, P primary equals V primary, I current primary. So if we do some manipulations here, we can see then if we take our relationships primary and secondary, and recall that we were shown that the current in the secondary is equal to the ratio of the current in the primary to the number of turns, and that V secondary is equal to N times V primary, then by substitution, if we substitute, you notice I've got them color coded here, let's substitute the red value in for I secondary, the blue value in for V secondary. Okay, so we put the secondary in terms of the primary. So the N's cancel out, we get V primary, I primary. So P secondary is equal to V primary, I primary, which gives us P primary. So it's just a relationship of moving terms around and solving one in terms of another. Okay, so when we come back, we're going to take a look at something called reflected load in a transformer circuit. Okay, and we're going to look at how the load actually appears to the source as a reflected load, as seen in these two diagrams.